All right, ladies and gentlemen, today we're going to take a look at the answer key for practice 17C, which is our first foray into integrated rate law. And so we have been practicing, hopefully you've been practicing on how to graph using your calculator, and what we're going to try to do is determine which of the equations a set of data conforms to. Remember that if the data gives us a graph when it's a straight line just by graphing time versus the straight concentration of a reactant, then it is a zero order reactant and it conforms to these equations. If it gives us a straight line when we graph time versus the natural log of the concentration, then it is a first order reaction. And finally, if we graph our data and get a straight line when we have time versus these should not be equal signs. Sorry about that. They should be versus. If we get a straight line when it is time versus the inverse of our concentration, then it is a second order equation and it conforms to these equations. So here's number one, and right off the bat it tells you that a plot of natural log of the concentration versus time resulted in a straight line. That means that this reaction is first order, and it's going to correspond to these data, these equations. Okay? So it says determine the rate law and the integrated rate law and the value of the rate constant for the reaction. So let's be careful, because when it says rate law, this is the original differentiated rate law that we started with. And of course, integrated rate law specifies something different. So the differentiated rate law for a first order reaction is going to look like this. Rate is equal to K times the concentration of A raised to the first. And since it is a first order reaction, we are going to use natural log of A is equal to negative KT plus the natural log of A at time 0. And since it's asking us to find the value of the rate constant K for this reaction, we would normally have to plug some data in to solve for K. It gives us an initial concentration of 2 times 10 to the minus 2 molar, but it doesn't give us any other data than that. So how are we going to determine K? The cool part about this integrated rate law stuff is that each of these equations, if you recall, corresponds to the equation for the graph of a straight line. And that means that if we know the slope of the line, we know K. Well, it clearly states that the slope of this particular line has a slope value of 2.97 times 10 to the negative 2 minutes to the negative 1. That means that that is our value for the rate constant. And it even gives us the units. So K is the slope, and it's negative because this graph would be sloping downwards. If it was a positive slope, it would be going upwards. So we'll eliminate the negative sign. 2.97 times 10 to the minus 2 minutes to the negative 1. Calculating the half-life is a pretty straightforward equation, because the half-life for a first order reaction looks like this: 0.693 over K. So we're simply going to plug those data in, and here's our calculator. So we'll say 0.6, oops, helps if I turn it on, 0.693, hang on, too many decimals, 0.693 divided by 2.97. We're eliminating the negative sign because the rate constant is not negative, it's only negative in the equation, times 10 to the negative 2. And here is our half-life. And since the rate constant k is in minutes to the negative 1, that means that our half-life is going to be in minutes. So 0.693 divided by 2.97 times 10 to the negative 2 minutes to the negative 1. That's inverse minutes, inverting an inverse, or inverting something in the denominator, puts in the numerator. And our value for our half-life is 23.3, and the unit is minutes, 23.3. Okay. Last one, how much time is required for the concentration of A to decrease to 2.5 times 10 to the negative third molar? So we're trying to find T. What we're going to do is we're going to plug these values in. Natural log of 2.3, 2.5. It's a Monday, ladies and gentlemen. 2.5 times 10 to the negative third moles per liter. And this is equal to negative K, which we know, 2.97 times 10 to the minus 2 minutes to the negative 1. We're trying to solve for T, and we're adding this to the natural log of initial concentration, which is 2 times 10 to the negative 2, also moles per liter. Don't even worry about the units, moles per liter, because they're going to disappear when we take the natural log. So to get T by itself, what we're going to do is we're going to take the natural log of 2.5 times 10 to the minus third. We're not going to worry about the units because they're going to disappear. We're going to subtract from this the natural log of 2 times 10 to the minus 2. And we will divide all this by 2.97 times 10 to the minus 2 minutes to the negative 1. So right off the bat, you know your answer is going to be in minutes. So let's take out our calculator. And I'll move this over here so it's no longer in the way. And we're going to say natural log of 2.5 times 10 to the negative 3 times 10 to the negative 3. Sorry, this calculator is a little strange sometimes, minus the natural log of 2 times 10 to the negative 2. I think there's another way to do this where if you are dividing two natural logs, you can just take the natural log of dividing one by the other, but we're going to leave it just like it is. So 2 times 10 to the, there it goes, negative 2. Let's take care of this right off the bat, and then we'll divide this by negative 2.97 times 10 to the negative 2. This should give us our answer in minutes, 70 minutes, 70.014. We'll just round that to 70. So how much time is required? 70 minutes. Okay, here is number 2. It says determine the rate law, the integrated rate law, and the value of the rate constant. The rate law, let's remember, is the differentiated rate law, and it is different from the integrated rate law, but the order is always the same. So once we know the order, we can just assume that that is the order for both rate laws. So we're going to plug this data into our calculator. It's a good idea to clear the memory. So I'm going to clear all these lists, and that way I know that I don't have anything in my data. So bring this a little closer. I'm going to put time in the L1 column, and let's make sure that we're entering these all correctly. and that is time, and that's in L1. In L2, we're going to put the concentration. So that's 1. Your calculator is going to eliminate a lot of this stuff, so you don't need to plug in the zeros. It does all that for you, but you do want to make sure that you have it all in correctly. I didn't want that. Make sure you have it all in correctly, because it'll screw everything up if you don't. And this is probably the most time-consuming part of the whole process. Okay, so what we're going to do is we're going to graph these data. We're going to go up here to stat plot, and we'll just start off with L1 versus L2. We won't do anything too fancy, but we want to make sure that it is on. And now that it is, we can graph. Remember that this is L1 versus L2, right? We want L1 on the X, we want L2 on the Y. And so now we can graph it, and we're going to zoom out to the data. So zoom 9. Okay, that is nowhere close to a straight line, so it is clearly not a first order reaction, or a zero, excuse me. It is clearly not a zero order reaction. So we're going to go and tell our calculator to take the natural log of the concentration. So I'm highlighting L3. And right now the calculator is asking us, what do you want everything in L3 to equal? I want everything in L3 to equal the natural log of everything that's in L2. So now that looks like this, and we'll go to our stat plot and instruct our calculator to graph L1 versus L3. So we're going to first go up to plot 1 and turn that off. Then we can go up to plot 2 and turn that on, and we'll modify it so that it is now, that's not what I wanted. Wrong button. That's what we want. Okay, so we're going to tell the calculator to turn on plot 2, and we're going to instruct the calculator to graph L1 versus L3. Now we can graph that, and we'll zoom to the data. This is a very straight line, and that means that this is very clearly a first order reaction. And so that means that the differentiated rate law is going to look like this. Rate is equal to K times the concentration of H2O2 raised to the first power, and natural log of the concentration of H2O2 is equal to negative K, which we don't know, times the time, plus the natural log of H2O2 at time 0, which is its initial concentration. We're going to get the value of the rate constant K, and we'll do it 2 different ways to verify that both of these ways work. So we'll pick a time, let's say 120 seconds, and the concentration is 0.91 at 120 seconds. So we'll say 0.91 moles per liter, this is going to be the natural log, equals negative K, which we don't know. We picked 120 seconds, plus the natural log of the concentration at time 0, which was 1. To solve for K, we're going to subtract natural log of 1 from both sides. Again, there's a way of doing this where you simply take the natural log of 1 divided by the other, but we'll leave it just like this so it looks like the equation. We're going to divide this by 120 seconds. The natural log will eliminate the units. And so our value of the rate constant K will have the units seconds to the negative 1. So we'll take the natural log of 0.91. We will subtract from that. Let's close off the parentheses. We'll subtract from that the natural log of 1. And we'll divide that by 120. And this will give us value units of the rate constant K, 7.86 times 10 to the negative 4.